Welcome. So, I'm Avi, Avi Pe'er. First, I strongly invite you to show your faces. There are so many limitations to Zoom. And by the way, the fact that you are in the class also with your face there is something that on one hand helps me feel that I'm not just broadcasting in the radio, and helps you be more committed, because when the camera is on, you are a little bit less inclined to just go to the refrigerator and take something. Yeah, then it's, so that's one recommendation. The question was before, how long will be the meeting? Well, we meet for 3 hours and then you have a tutorial afterwards. So 3 hours don't end at 8, they end at 7. We will, but it's 3 academic hours. So basically we are meeting for 2 hours and 15 minutes, but I think it would make sense to have a break in between. So we'll try to go something around an hour 15, somewhere in between. And if I'm losing myself, then you can stop me and tell me, Avi, what about the break? And then we'll take a break of, I don't know, 10, 15 minutes and continue. So we should, so the plan is to be here overall 2 hours and a half. What else? Okay, in terms of your I don't know, rather, you're adults and you know how to find me. So I'm sure that you can find my email and my phone number and my home address and whatever method you would like to contact me, you're welcome to use. I will be available. So if you have questions, you can ask them, or we can arrange meetings personally. So don't worry. One more thing is the tutorial is set for the evening today. It doesn't have to be there. You're not so many students. I'm not sure that it is very convenient to have a tutorial between 7 and 9 in the evening. So if I mean, this is the time. If it is inconvenient to somebody, then it will remain that time. If somebody prefers it like this. But if all of you do prefer to move it, then you can agree on this with Leon, and it can be shifted. Even for myself, I'm willing to move the hour of the lecture. It doesn't have to be Tuesday between 4 to 7. And I do suggest, I'm sure you can find each other and open some WhatsApp group for the, and figure out if you would like. There's only 9 students registered this year. If you prefer to have the lecture on some other day, it can be done. My limitations are Tuesday morning out, Monday morning out, afternoon is okay. Well, Wednesday around noon, we have a seminar. So Wednesday, either afternoon or early in the morning. Okay. So something about how the course is organized, and we'll start with real physics real soon. you will have, so there's no exam in the end of the course. There is a project or final project. Now there will be exercises during the course, something like 5, maybe 6. You'll submit them, they'll be graded, and they'll compose 50% of the grade. The other 50% is the final project, which you'll get. So it's basically another exercise, which may be a little bit larger, and it will be limited in time, but and that's another 50% of the grade. So that's how things work. Anything else we should talk about before we start to really talk? I don't think so. Okay. So let me tell you what we're doing. Wake up. Okay. There's one thing that I did want to say, and that is that I hate Zoom. I really do. And I strongly prefer to have those meetings in a room where we can actually, can really interact. So I asked, as soon as it will be possible, to have to arrange our meetings to be in one of those hybrid classes. I don't know if it will be possible, but this is something that I really hope will be possible, so that we can meet. The ability to connect from home will still be there, but I think there is great value, definitely for me as a teacher, but even more so for you as students, to be present in a class and not learn over Zoom. So assuming that, the vaccines work like a miracle, and we are assuming that all those who are vaccinated will be able to come into the class and have a meeting. And those who prefer to connect from home, those are hybrid classes, so they can. So I'm trying to have this arranged. I'll let you know once I know, hopefully, I hope by next week, but I know that the plan in the university is to go back to teaching, to standard teaching in classes after Passover. And if we can, we will as well. So I'll share the screen or my tablet, and then let's get out of here and open. Okay, let's make it smaller a bit. Okay, so we're talking about quantum optics. Well, I meant to have it colored differently. Okay. And then it's a question of what do we mean by quantum optics? Before we start, can somebody tell me what is a photon? And those who think they know the answer, okay. Asar, if you're trying to talk, then we can't hear you. really, I do want to ask you, and
I can.
Type of a boson. Well, now you're defining one name by giving it another name.
It's kind of a particle of the light.
Particle of light.
Maybe quanta of light.
Okay, but what does it mean? So we are asking ourselves, what is a photon? And we have an answer like a particle of light. This is what?
Electromagnetic field.
But what about, we're talking about a photon. There's something like quantum here that
when we look,
when we talk about, just a minute, you were saying electromagnetic field. The electromagnetic field is classical. You don't need a photon for it. Now, when we think about a particle of light, what does it mean? There is a small ball with an h bar omega written in it. And it flies here. It has a mass of 0. And it flies at the speed of light. Is it?
It's supposed to be the light itself.
We'll discuss this. This, I'm sorry to disappoint you. No, this is a very bad impression. It is very rarely useful and most of the time harmful. Because if you think about a particle, you think of something localized. And there's very, very strong problems about talking about the localization of the photon. There were, and then we can say the quantum, the quanta, but let me ask you something else. How do we know that a photon exists?
Because we have some experiments in which we can see the optic ray, it behaves like quantum of energy, quantas of energy.
Wait, okay, but tell me which experiments?
The photoelectric one.
Photoelectric effect.
Yeah. So we can explain it by saying there's quantas of energy, and we call them photons. So. And about the localization, I mean, in quantum physics, we're talking about particles, and we say there that there is no specific location, right?
But when I talk about an atom or an electron, it does have. Wait, I'll explain a little bit more. Right now, I'm teasing you to show you how many very standard concepts you have that were taught to you over the last few years that are unfortunately wrong. Because, by the way, the photoelectric effect, does it tell us that there is a photon? Meaning now, and surprise, and again, the answer is no. Why? What happens in the photoelectric effect? In the photoelectric effect, we have, I don't know, you have a cathode, you have an anode, which only means that, and they're connected to a power supply. So here is the plus and here is the minus. Or sorry, the other way around. So this side is charged positively. This side is charged negatively. But everything sits in vacuum. So basically there is no current. And now what happens is that light comes in. Oh, let's give it a different number. Light comes in and hits the cathode. And what do we see? It releases. So this is the very original photoelectric effect. Since then, it's been realized in many, many platforms, but let's think of this. It releases an electron. Sorry, let's use a different color for the electron. And this electron is accelerated in this electric field and hits the anode, and then we see current. So if I put here a measurement of the current, I'll see the current forming. Indeed, I will see clicks. Whenever an electron is released, there will be one electron of current here. If my measurement is sensitive enough, I will see that there are discrete electrons in there. And the photoelectric effect will show a discrete nature of detection. Every time light comes, I'll be able to measure 1 or 2 or 3 or many, but in any case, never a fraction of an electron. It will be an integer number of electrons. You know why? Because electrons are particles. Electrons, not photons. The photoelectric effect shows you that the electrons are quantized, not the light. There is indeed a work function. You need to have sufficient energy for the light in order to see if the energy, if the frequency of the light is not high enough, it cannot release an electron. There's an energy gap. But all of those are properties of the matter. Here, there's quantum matter. And the properties of this material dictate the, so if you're looking at the photoelectric effect, does this tell you that a photon exists? No, it tells you that an electron exists. There was radiation. Radiation hit the cathode and released an electron, or 2, or many. But do you know that that this radiation was composed of particles of light? No. So the photoelectric effect by itself is not a proof of the existence of a photon.
You can do a beam splitter experiment and try to find a single photon coincident detection.
Okay, then yes, but okay, so we'll discuss this in a moment. Let me just close the door though. Okay. So, so the photoelectric effect doesn't really prove that the photon exists. It proves that electrons exist and that they interact with light. or with an electromagnetic field. We have an electromagnetic field heating the cathode, and it releases electrons. So, okay, I'll tell you in a moment what experiments really do show that you have single photons. But what else? Have you ever heard that the black body radiation, or that black body is the proof of the existence of photons, or discussed as the emission of a photon or the absorption of a photon?
Yeah.
If they say that if it's not a single quanta of light, then it diverges at low frequencies. Right?
No, but then we should be careful. Indeed. So what I want to say is, okay, we'll discuss this. Let's first discuss the question of what happens. We're going to talk about black body radiation a lot today. But what I want to say is that indeed, what was Planck doing? He said that you want to understand there's a black body, which is matter, and it interacts with the radiation. What Planck said was that the emission of radiation or absorption of radiation comes in quanta. This was critical, indeed. And we'll remind you of this in a moment. But look, there are two sides to this. There's a material body and there's the light. Now, those two, something dictates that the interaction between them will be quantized. And it will be so that the energy will be emitted in quanta and absorbed in quanta. Discrete quanta. This is what Planck tells us. But which of them is the quantum? If the material is quantized, if the material is composed of single atoms that can emit or absorb only finite amounts of energy, then who said that the radiation is composed of quanta? The radiation is the radiation. What I want to say is that all those experiments, they are experiments of light, matter, interaction. And they are indeed quantum. But which is quantum? The light or the matter? Or both? And the experiments that we just described don't tell us or don't require that the light be quantum. Here there is something that needs to be understood. So I want to, for a moment, to think about what is quantum. And you've learned quantum mechanics mostly for matter. So you quantize the hydrogen atom and you know how to solve it quantum mechanically. And you've heard about the double slit experiment. When you do it with electrons, it's a proof of quantum mechanics or something like this. But let's remind ourselves. So I can ask, okay, I can make a table. So I can ask myself, what is quantum and what is classical? I can ask this for matter. Now then, oops. First of all, when we think about something that is classical and then we can ask the same question for light. So when matter is classical, it acts like particles. And it follows, I don't know, and it acts like particles and it doesn't show any interference. But when matter starts to behave like waves, and you can see interference effects, then we can say that matter started to behave quantum mechanically. But what about light? What is the classical representation of light?
Waves.
Electromagnetic field.
Right. So it's really the other way around. When you see waves, when you see interference, a double slit experiment with electrons is a quantum mechanical proof. A double slit experiment with light proves nothing. Light is a wave. You can, okay, so I'll reduce the intensity very low until I have only single photons. How do you know? I put a detector and it gives me a click. Well, a click is not a photon. A click is an electron. So the fact that, so what I want to convey to you here is that the notion of a photon is something that we take very lightly, but it's not so simple. And especially from the case of experiments, how do we even know it exists? The very common two examples, black body and photoelectric effects, are both wrong. They don't prove anything about the existence of particles. When light starts to behave in a particle way, and I'll put it in parentheses because it's not, it's not really particles. Really, there is things become quantized. And we'll ask ourselves, what exactly is quantized in this case? So this is something that you should remember. If somebody shows you a very complicated interference effect, tells you, see, this is a quantum effect. Well, no, or not necessarily, because interference is a classical property of light. Only when you have things that remind you of particles, this is when you should see something like this. Let me tell you about which experiments can show this. And that is, suppose that I have a single photon source. It's an atom. I don't know if there is something like this, single photon source. Do I have it? I don't know, maybe. But I want to show you how I can prove that it is. It emits light. Let's assume that, it emits light in different directions, but I collect it with the lens and I'll take the light going that way. And here I'll put a beam splitter. Meaning that it splits the light 50-50. And then I'll put not just one detector, because as we said, one detector tells me nothing. One detector tells me, okay, I see. What do I see here? I don't see the light. I see the electrons. Even for us, our eyes are an array of photodetectors, which do what? absorb light and generate a photocurrent. So what we detect is always the current here. But now I can, there's a beam splitter, so there are two outputs, and I can put a detector here and detector there. So I'll get the photocurrent here and I get the photocurrent here. And then now the question is, what do these two detectors click together? Can they click together? Now, if you do a classical analysis, and the beam splitter is just making two copies. So, if I have here an amplitude A, I'll have here an amplitude A over square root of 2, and here another one A over square root of 2. So this is just a weaker version of the light. But if here there is an intensity and there is a probability to generate a photon, not a photon, an electron, then there's here another, also the same probability. So we should expect that there will be cases when the two of them will click together. When if I take those two and I multiply them one by the other, I should get something that is non-zero. There is a probability that those two detectors will generate photoelectrons at the same time, because they are looking at the same light. But if we think about this quantum mechanically, then the answer is no. They will never click together, assuming that this is truly a single photon source. If this source emits single photons on a random basis, I don't know, every once in a while it emits, but a single photon, just a single photon, then quantum mechanically, there is a 50% chance that it is here and 50% chance that it is here. But if it is a photon, if there is truly a quantum an electromagnetic quantum, then it is either here or there, but not in both. So a single photon will show never coincidence. So if I ask myself, what is the result here? I plot this. Sorry. I'll plot here the probability of coincidence. Let's call it P2. This is the probability of coincidence. As a function of what? Of the relative delay between the two detectors. So I'm asking whether, if they both detected at the same time or at different times. Now, if you remember, if this is emitting just a single photon, then they will never have coincidence. But if this is indeed a source that emits randomly, every once in a while it emits a single photon, and then it sits down for a little while and then emits again a single photon. Then if the delay is long enough, then maybe one detector caught one photon and the other one caught another that was emitted later. But at the same time, because there is always just never more than one photon, but at the same time, they will never coincide. So you will see something like this. At 0 time, the coincidence probability goes to 0. And at larger time, it goes to some value. It can be high or low. It depends on the flux of single photons that you generate. But, and it will have some width, which is somehow the duration of a single photon. Okay. So this is an example for an experiment that can show you that the photon exists. And look here, we had to work in order to identify this because a single detector doesn't tell us. It shows a click, but this click, is it related to the existence of a photon? Not necessarily. Only the fact that you put two detectors in front of the same light and show that they never click together, this is something that cannot be understood classically. This is a place where you really need the photon. This is called the quantum Hanbury Brown and Twiss experiment. How many people are Hanbury, Brown, and Twiss?
3.
Those are 2 people. One of them is called Hanbury Brown, so this is one name. And the other one is Twiss. So there's 2 of them. We'll discuss the Hanbury Brown and Twiss experiment, or it's also called what we say anti-bunching. That's another name for this experiment. Why anti-bunching? Because you click here or there, but never together. We'll discuss the Hanbury, Brown, and Twiss experiment. Well, not today. We'll take some time. So the course deals, as we said before, but let me write it again, about the quantum light matter interaction. And then we'll describe situations where the matter is quantum and the light is classical. This is what we call the semi-classical theory. We will understand this because it is very important to understand the classical interaction very well in order not to speak stupid things. I think that one of the things that was very, very important was that in my very first year, I met a teacher. He was teaching me, his name was Yona Oren. I'm not sure he's still alive. He was very old at the time. And since then, I'm still young, but young for a long time. He was very frightening. And it was, I was shaking just to come and talk to him. He was teaching us, the introduction to modern physics. So he was teaching us relativity, private relativity, first year. And there was a question, there was a paradox that we were trying to analyze and I couldn't understand. And he said that there is a time, an hour where we can come to talk to him. And I decided that maybe I'll come over and ask him about this question. So I brought the exercise that we were trying to solve. And I was asking, now he didn't solve anything. He didn't explain anything about how to solve the problem. But he told me something that took me a while to understand that was very, very critical and important. First, solve classically. If you want to understand relativistic effect, first solve Newtonian. Solve the Newtonian case, understand it completely. ask yourself what happens in the Newtonian case of your problem. And then when you understand this, it will be much easier to understand what is known, what breaks down. So to analyze classical light in its interaction with quantum matter is very important in order to then, so this is the first third of the course. And then we have another third of the course where we describe quantum light on its own. And in the end, we will try to discuss the quantum interaction. So this is quantum light or quantum field theory. Quantum field theory of electromagnetic lights, fields. And once we quantize the electromagnetic field, then we will maybe start thinking about the quantum interaction of both, when both light and matter are quantum, and what is different in those cases from the semi-classical. So when both of them this interaction will be the final part of our course. Okay, so I'll tell you what will happen now, but I think we'll take a short break soon. And then, so we're going to start discussing the field, the light matter interaction. So for today, we're going to discuss light matter interaction. And first, we're going to review very briefly the black body and Planck, and say where things look like photons but are not. Then we'll start to discuss the two-level system. What we will do today is we will discuss Einstein coefficient. Those are things that I think many of you learned somewhere. So this will be a quick review. The point is that this will be an entrance to start talking about other forms of the two-level system, but this will be the next few lectures. So now we're going to take a break because I need one. So we'll have it, okay, now it's 10 minutes to 5. Let's meet again at 5 and continue. So yeah, so I'll pause recording. Okay, so we are now, we want to, there was one thing that I forgot. And that is to tell you what is the book that we're using. So, well, I'll write it here. Book of the course. Honestly, there isn't really just one book, but in many things I follow Loudon. You can guess the name of the book. Introduction to Quantum Optics. There are other very good books, many of them. So on the, you're welcome to take a look. There's Yariv, Amnon Yariv, Quantum Electronics. There's many others. There's the book of Alain Aspect. I don't remember. He's French. So there are many good books. So I'm not going to send to you to one of them. Loudon is the one that I follow most of the, but you don't have to take it because Loudon is, you know, he's very deductive, but on the other hand, he's a theoretician. So at least, you know, I use him for the lack of a better option. But okay. So yes. So let's remind ourselves a little bit about the very, you know, quantum mechanics was born from quantum optics or from the quantum interaction between light and matter. The black body radiation is indeed a case where, you know, that's the birthbed of quantum mechanics in general. But and here, and the point is that if you remember how black body works, so we're going to discuss black body and Planck. So I'll remove this from here, and this is what we're going to talk about. So I remind you that, you know, we start from a cavity. We assume basically a cavity of material, cavity of matter. So we always think, we know we're physicists, we like to think in Cartesian coordinates, so we have a box. And this box is full of radiation. So this cavity is the material, it's matter. It has a temperature T. And it interacts with the radiation inside the cavity. So it can emit radiation, it can absorb radiation. Well, why? Because, you know, matter is made of charges. And when the matter is at a temperature T, those charges are moving. And when charges are moving, they emit, classically, they emit an electromagnetic field because, well, charges are moving, they're vibrating, and then therefore they are noisy, and they emit an electromagnetic field. And also they can absorb the electromagnetic field. If there is an electromagnetic field, it can move the charges. So they interact, the charges in the matter interact with the radiation inside. Or electromagnetic waves inside. And then, so yeah, cavity, so the walls, they're at temperature T, so there are fluctuating charges. Which means that they emit radiation and they can also absorb radiation. And we would like to analyze the, the steady state or the thermal state, thermal equilibrium of this light matter interaction. And then we could say, well, this is a cavity. So if we think of this as a cavity with a, you know, which is an L by L by L length, then we know that within this cavity, not any electromagnetic wave can exist. Only modes of the electromagnetic wave can exist. So in a cavity means that there are electromagnetic modes. In this case, they are very simple. I mean, if I look at the electromagnetic, the field we should be careful about, well, the field, it has a polarization. So I can ask what is the X polarization of the field or the Y polarization, but as a function of R and T. And I could say, look, it has, it looks like some amplitude, some Fourier amplitude. And then a mode. Now you've done this already. I mean, I'll very quickly. Now, why is this a cosine and why is those are sines? That's not important. Conceptually, they could all be sine functions or cosine functions. The point here is a little bit the fact that the electromagnetic field is a transverse wave, and you know, and X is the X polarization. Of course, and it could be polarized in X, they could be polarized in the other direction. It also has some propagation. So there is this relation of the two polarizations and the axis of propagation, or the axis of what we call Z, then this is what makes the difference. But this doesn't really matter. And K, as you know, well, R is the vector of X, Y, and Z. And K is the vector of Kx, Ky, and Kz. And we know that those Kx, Ky, Kz, they cannot be any value because of the mode structure of the cavity. So Kx or Y or Z is related to the length and times an integer. So n. So there are three integers, nx and y and z. I tell you, but those are they don't have anything to do with quantization of light. This is just the classical electromagnetic mode of the electromagnetic wave that lives in this cavity. And according to the boundary conditions, those functions are dictated. Let me remind you of the density of states. So we could say, look, there's I can plot three-dimensional graph of Kx, Ky, Kz. And as we know, we have a situation where both of them are zero. Then we have another one at pi over L for X or for Y or for Z. And of course, we could have also, like, it's like a grid of possibilities. For example, this is the case 2, 2, 0. So here we have 2 pi over L, of course. And I can, basically there are states like this here as well. And here, and it's a grid. Sorry, what I want to do is this and this. Those two, they're out. And this, and I do this. So we have a three-dimensional grid. And they are separated by this pi over L. We can ask ourselves, okay, so what is the density? Now then suppose, you know, and now, so we and this is something that you've seen many times. We can ask ourselves, what is rho of k dk? Now this is the amplitude. So k is the square root, pi over L is out, and then nx squared plus ny squared plus nz squared. So this is a sphere. And we ask ourselves, what is this density of states? And well, we know this is 4 pi k squared. This is the surface area of a sphere with a radius k. You know, I'll take here a sphere with a radius of k. Times dk, and then times, okay, so pi over L to the power of -3. Why? Because this is, what is one state? Each state holds a block of pi over L in both directions, in all directions. And there's also, oh, what did I do? I made the balagan. Okay, I tried it again. This is the shell of width dk times, now here comes the pi over L to the power of -3. And there's also times 2 for 2 polarizations. So we can say now that rho of k is a quarter for, no, a quarter, no, not a quarter, nothing, sorry. Quarter and 2, they go with 8. And so this goes like pi k squared dk times pi over L -3. Now, usually we calculate this per unit volume. So if we do it per unit volume, we divide by the volume of the cavity, which is, so 1 over L to the 3. Now here L is at the power of -3, and here L is to the power of 3. So those two, they go away. And so this is per volume. And then we can say that, you know, rho of k, and then is k squared divided by pi squared. Oh, sorry, then this dk should not be here. Or keep it on both sides. I can convert it, of course, to omega, remembering that, you know, omega equals ck. So that means that d omega equals c dk. And then, therefore, rho of omega, d omega equals omega squared divided by pi squared c squared times d omega. I can talk also about, you know, remember that we can remember that lambda equals 2 pi divided by k. And then that means that we can, from this, we can say that d lambda equals 2 pi over k squared dk. And we can then write rho of lambda d lambda equals, and you can do it yourself. You've done it several times, I guess. All of those are that's the density of cavity states. Now, we can talk about the total, sorry. So, and we can talk about the energy density. The energy density. In the state, again, it's a reminder. This is half epsilon 0 E squared plus 1 over mu 0 B squared. Or I can say that the total energy is the integral of this. Over the volume. And then now we can remember, but you know, the fields, there is a relation between the fields. So for example, I can remember that Maxwell tells us that curl of E equals minus dB to dt, which makes, you know, let's do a Fourier transform of this. That means that K cross E equals minus I omega B. Now, if we want to, so that means that in terms of size, this K times E.
Shouldn't it be IK?
What?
IK vector?
What do you mean?
The Fourier transform of...
Right. Doesn't matter for what we need to do, but yeah. Omega times the size of B. And what it means is that basically, since here what we have is only the B as it is, then I could put here basically saying that if I look at the average, then I can really put in here, and you know that omega divided by K is C. So I can take this and put it back here, and to say that the energy is really half, well, integral dV epsilon naught squared E squared plus 1 over mu C squared. Again, E squared. Now, then this by itself is again epsilon, because, well, you know, C squared is epsilon naught divided by mu naught. I think, but in any case, what we're going to end up is with this being integral dV. If I just look at what we call the average of this, average over one period of time, one period of the wave in time, then it will be just this. Because the fields are related, because B and E are related, basically you need to know only one. The other one is generated by itself. If you know the electric field, then the magnetic field is known as well. So just electric field intensity or the magnetic field intensity. For this, for the sake, we'll tell you everything about the. And now we can talk about what is the energy of each of the modes. So this is per mode. I can calculate. So UK, tell me which K you're looking at, is related to the electric field of that mode. This is the energy, oh, sorry, not in Hebrew. Energy of mode K, which is basically, as we said, pi over L, Nx, Ny, and Z. And this is the electric field. Oh, yeah. Let's write it like this. Ek, the energy of K of R and T. Okay. So, and now Planck realized that, yeah, there is a problem. What is the problem? The problem is the following. Classical thermodynamics tells us that every degree of freedom will be in a thermal equilibrium, will have an energy of half kT. So the problem is classically thermodynamics. Classical thermodynamics tells us that, you know, half kT per degree of freedom. Which in this case means a mode. But how many modes are there? Infinite. So if each one of those electromagnetic modes has a half of kT energy, so UK on average should be this. But the number of modes is infinite. So the total energy in the cavity diverges. Every mode, no matter what, will have half kT energy. In fact, it will have not half, but 1 kT energy because it is has two polarizations. And that is a problem. Now, let us remember what's the difference between the modes. The difference between the modes is their wavelength or frequency. So low, there are the basic modes, they have a very low frequency. And then there's the high modes, and there's an infinite number of them, the higher modes. They have a much higher frequency and shorter wavelength, higher wave vector. And what Planck tells us is that again, where does this half kT come from? It comes from the interaction with the matter. The matter has is emitting radiation and absorbing radiation, and it sits at this temperature. So therefore, it must like this. And then what Planck said was that no, the energy, so Planck tells us energy is exchanged between I don't know, walls and cavity, or matter and light, only in quanta. So this U only in quanta, so UN, now N being the number of quanta that were exchanged, that the matter, so therefore, because it is exchanged only in quanta, then this mode K we wrote it before UK like this, but here I'll put another N, meaning the number of quanta that is there. We had N before for something else, but never mind. I mean, we can't, that equals H bar omega. This is the size of the quanta times N. Omega of K, of course. So this does not say photons. This could be due to the matter. The matter only can emit some amount of radiation and absorb it. This doesn't say that this emission is a particle. And then here the point is that this H bar omega, it goes up with frequency. So in order to emit a quantum of light or to release into a high mode, you need a lot of energy. And to a low mode, you need a little bit of energy. Now, thermally, it's very easy to have a little bit of energy, but it's hard to have a lot. So the question now, this omega, this H bar omega gives a scale. The question is, what is H bar omega relative to KT? Is it larger? Is it smaller? Is it equal? And here the point, and as you all remember, we can say that, you know, the probability to have n quanta in a specific mode now, then that in the thermal equilibrium equals e to the minus the energy of this mode divided by, ouch, now we have this K and this K. Here, this one is Boltzmann's K.
KB.
What? K Boltzmann, yeah, right.
KB.
Boltzmann. And here we had Boltzmann as well. And of course, we need to normalize by the canonical partition function. Now, okay, and then there's this standard trick that you all know. This goes like, now this is here, so this is e to the minus n h bar omega, and then beta is 1 over kt, divided by sum over n e to the minus h bar omega beta again times n, well, you know, so let's call e to the minus h bar omega beta, let's call this I don't know, alpha. So this equals alpha to the power of n divided by what? The sum of alpha to the power of n. And this, as you know, is alpha to the power of n times 1 minus alpha. Times, or yeah, true. So there is this alpha, which is e to the minus h bar omega b beta. And so this is the probability. And now I can calculate anything that I want. For example, what is the average number, or let's call it, sorry, the average u of that specific mode, of course. This is h bar omega times the average n. And so this is h bar omega times what? Times sum over n, n p of n. And this we know, so you know how to calculate this. So this is, yeah, Pn, we know what it is. So this equals, well, there's h bar omega out, and then there's 1 minus alpha here. And then there's the sum of n times alpha to the power n. This goes from 0 to infinity. And we can calculate this. And you know how to calculate this. This is simple because we realize that this is equals to d to the n, no, d to the alpha of the sum of alpha to the power n, which is d to the alpha of 1 over 1 minus alpha. You know this trick, and you can derive this, and then that means that we can say that the average energy of a specific mode of frequency omega equals, we can calculate it, it turns out to be u, sorry, yeah, not u, what I meant was alpha divided by 1 minus alpha. Check me after you derive this and put it back in there, which is, of course, times h bar omega. And therefore, this is h bar omega times e to the minus h bar omega beta divided by 1 minus e to the minus h bar omega beta. This is the famous Planck formula, which tells us that the energy of a mode is not half kT, but actually less. I mean, we can take this on different, different, so let's see, this u, what does it go to when omega goes to 0? When omega goes to 0, it becomes, then it appears to diverge. No. Well, let's see. We have, yeah. Yeah, sure. Sorry. When omega goes to 0, then we have here h bar omega divided by what? By 1 minus h bar omega beta, which is basically 1 over beta, which is kT. It should have been half, but we don't care very much about factors of 2. So that part makes sense. But the fact that if we ask ourselves, what is the average going to when omega goes to infinity? And then it is much less. It goes to h bar omega indeed, but then we have an exponential. So this is much less. So it basically goes down to 0. This is what we call the freezing of the degrees of freedom. All frequencies that are high are freezing. What's the scale? Again, as we said before, what sets the scale between those two? This parameter. Is this h bar omega beta, is it larger than 1 or smaller than 1? Which is to ask, what is h bar omega relative to kT? And as you know, the Planck constant is a very small number, but it's not 0. We can also ask ourselves and remind ourselves, what are the fluctuations of the number? So, so we can write, as we said before, if I say that n, the average number of n equals alpha divided by 1 minus alpha, which indicates also that alpha equals average number divided by 1 plus the average number. Check it. Which means that we can write this Pn as being, well, you know, we had it alpha to the power of n times 1 minus alpha. And this, you're welcome, to verify is the average n. This, what we had here. The average n divided by average n plus 1, this to the power of n. Oh, no, sorry, there's something else. This is to the power of n, this is to the power of n plus 1. Now, what is this? This is a geometric, this is a geometric distribution. So tell me the probability of n quanta at a specific mode is related to the average number. And as you can see, if the average number is high, then this probability is nearly 1. There are many, it's extremely broad. So average n divided by average n plus 1 is nearly unity if average n is large. And this number, it's almost, yeah. So it's almost like 1 divided by, you know, n plus 1. So, and then we can ask ourselves, what is the variance? It can be related, of course, to the, I can ask, what is the, I would ask normally, what is the variance of U? But this is, of course, h bar omega squared, the variance of n. Which, as we know, is the average of n squared minus the average of n squared. Or as we wrote before, we should put standard. So this is the sum of n squared Pn minus the sum of n Pn squared. Well, we can do the calculation. I don't want to bother you with this. It's simple and straightforward with tricks that you've seen, I think, more than once. And we will find that this equals the average n squared plus this. Or, in other words, the delta U, this is the variance. And this is the standard deviation, which is just the square root of the variance. There's, okay. You understand what I did here. There should be, of course, this h bar omega squared all the way through, but let's forget about this. So, you know what I mean is, yeah. Let's do this, take this thing. No, what did I want? Never mind. So if I ask myself, this is what delta n squared is. And if we want to know what the standard deviation is, so that's delta n equals square root of that. Or sorry, let's write it as the square root of n average times n plus 1. Now this is something that appears to be quantum, but look, there is this n average. Now n average is not necessarily a number or an integer number. Okay. But what I want to tell you is that those fluctuations are huge. Okay, so those are, now so that was a very quick reminder of how Planck and Planck quantization comes about and where this freezing of the degrees of freedom come from. Now, let's start talking a little bit about the interaction. Okay, so this was the following. We have matter in the walls. We have many, many modes in there. This matter interacts with all the modes. And it can emit radiation into those modes and absorb radiation from those modes. And from the quantum theory of exchange of energy, nothing about particles, only exchange of energy. And who is to blame for the quantum nature? We don't know. It could be the matter, it could be the light. But still the exchange is quantized, and this brings us to solve the black body problem. But now, so now we want to discuss the interaction of just a single mode with a single frequency with the atoms that emit it or absorb it. So we're going to do the simplest possible treatment of a two-level system. So these are we're going to discuss Einstein coefficients. Einstein coefficients, which is the simplest so it's there's A and B. It's a phenomenological theory of the exchange of energy between what? An atom but in terms of atom, I really should say a two-level system. With a single mode. Now, of course, the energy goes in both directions. Oops. It's a single, no. No, come on. Electromagnetic mode. So, what do we say? Now, what do we assume? There is this quantization. So we say, look, I have a medium. Now this medium contains n total of atoms. And we're looking at their interaction with a specific electromagnetic mode. And by the way, from the photoelectric effect, we know that there is a relation between the frequency of the light and the energy of the matter. So what we know is that to release h bar of omega of energy, we need h bar omega to match the energy separation within that matter. So we have n total atoms, out of which n1 are sitting at the, excuse me, at the ground level, and n2 are sitting at the excited level, and they can absorb energy. If they absorb, then this is absorption. So they go up. They can emit. And another thing that is purely phenomenological. By the way, it does not exist in classical theory, but is known to happen for reasons that we now do not understand, and will take a long while for us to understand. We have also spontaneous emission, meaning that an atom in an excited state can spontaneously emit So we call the first one stimulated emission. And the other one, spontaneous emission. Now, what Einstein did was to say, okay, let's just look at those populations. I want to count atoms. And I want to say something on the thermal state of the matter. And this is the main thing that he knew. He knew that the thermal state, oops, what happened? What did I do? Yeah. The thermal state of the matter is the following. And the number of atoms in the excited state relative to the number of atoms in the ground state, this has to do with this. This is the thermal condition of equilibrium. So thermal, not thermal state, let's call it at thermal equilibrium of the matter. This is the one thing that he knew. And then he wanted to relate this to what we just said. What does this say about the state of the radiation? And here we can, so now we can say the following. These atoms, they interact with an electromagnetic field. So we assume that we can say that, you know, now let's say U is the energy density of the radiation. Meaning per unit volume.
Avi, can I ask a question?
Sure. Everyone can ask a question every time, whenever you want.
You said that there is a spontaneous emission that we don't know the reason why it happens, right? At that point, in this point.
Right.
Do we know in this point what is the reason of the other emission?
Sure. That's actually easy.
Can you remind me?
Classically, you know, okay, as we said, what is an atom? It's an electron, and those are two charges. Now, here comes an electromagnetic field.
When it gains energy, so it goes up.
If you pass energy from the field into the vibration of this atom, this is a dipole. A dipole in an electric field, in an oscillating electric field, will oscillate. It can either absorb the energy or emit it.
So what is the difference when we're talking about spontaneous emission?
That it happens, it emits by itself.
With no energy around?
There's no field around. That's the point. A dipole, an electromagnetic dipole, classically, when you don't shake it, doesn't do anything. And the surprising thing is that spontaneously, if you have atoms, or let me put it like this, we will discuss this further during the course. You will see exactly where that dipole is. But when you have, you know, for now, this is just, you know, these are just, it doesn't, the theory of Einstein does not relate in any way to the source of it.
Mm-hmm.
But the fact that, you know, you have atoms and you shine light on them, it induces a dipole, and this dipole can absorb light. So it's a classical effect. Absorption is completely classical. Stimulated emission is just the same thing played in reverse. I mean, if you have excited matter, then it can emit energy into the field. But the point is that you need a field to be there. Everything is multiplied by the field. If you have a strong field, you have strong absorption and strong emission. But if you have no field, then there should be none, classically. We'll see this very soon.
Okay.
And the fact that spontaneously an excited atom just by itself, doing nothing, eventually falls down, we don't know why.
So we assume it because we know that in other experiments, we saw that without a electromagnetic field, we saw spontaneous emission. So
Correct.
Now we assume that there is one. Okay, thanks.
Exactly. Then, so what I mean is the following. Classically, the atomic levels, they are like shells, or you know, if I sit on the table, I don't spontaneously fall down to the ground. I can stay sitting there forever. There is no lifetime for sitting on the table. But what is surprising for atoms, it appears to be like this. I mean, the atom is in an excited state and spontaneously it falls down, and it's not clear why. But I can say that the energy density is what? I can relate it at frequency omega. I can relate it to the thermal. I'll write thermal now. And there would be, no, sorry, not equal, but plus some external field that we can put there. But this part must exist. This is the one that comes from the equilibrium between the oscillator, or the set of oscillators that are sitting there, the set of atoms that are sitting there. And external would be something like I turn on a lamp, I bring in a laser, I do something to introduce some additional light into this. But the thermal part always exists. Assuming we are in thermal equilibrium. Now we can say the following. So what Einstein did, he said, okay, let's associate coefficients to these effects. So let's say that A is, we're not talking in Hebrew, so we put it like this. A, what is it? There's going to be A and B. So there's going to be A2, 1. This is the spontaneous emission. This is the probability of spontaneous emission per atom. Now, it's not really a probability. Let me say something different. It is related, of course, to a probability, but it is really the lifetime. What do we mean? We just said, phenomenologically, we know that an excited atom doesn't stay excited, it eventually falls down. Why? I don't know why, but that means, now, I could say a lifetime, but actually what we mean is that 1 over the spontaneous lifetime. This is just a definition. And then I can say, and then there's another one, there's a coefficient B2, 1. And there's a coefficient B1, 2. What does it mean? It means, okay, tell me what is, I'll tell you that the probability of absorption, sorry, if this is 2, 1, then it's emission. Then let's call this one 1, 2, and this one we'll call 2, 1. The probability of absorption equals what? This coefficient times the energy density. Oh, we call the energy density U, so it will be U. And this is the probability of emission. That equals B to 1 times the same thing. Tell me what is the energy density. That is the probability of absorption. If there's more light, the probability is higher with some coefficient. And this is the probability of stimulated emission. Okay, so a priori, we have 3 coefficients that are not related. But now we're going to invoke to say something that takes into account this. We're going to say what? So this is the probability of emission and the probability of absorption. And there's an excited state lifetime. And now I can, so now I can write the following. I can ask myself, how much does the number of, say, ground state atoms change as a function of time? Well, that's obvious. That will be, if, so now we have a situation of N1 and N2, atoms in the excited state and the, or you know what, let's think about what happens to the excited state. Well, of course, those atoms can just spontaneously fall down. So we can have minus A to 1 times N2. If an atom is in the excited state, it can fall down into the ground state and disappear from the excited state. So this is a loss. And now you can see that indeed the dimensions of this coefficient A must be 1 over time for the dimensions of this thing to work. And then maybe there is some stimulated term. So there could be also some stimulated emission. So that would be proportional to N2 again, times B to 1 times the density U. And there also could be absorption that introduces atoms into the second level, which equals to N1, how many atoms are in the ground, times B12 times U. And of course, if I ask myself, what is dN1 to dt? So as we said, N1 plus N2 equals N total. The total number of atoms doesn't change. So this is just minus dN2 to dt. So now, so let us say the following. At thermal equilibrium, then the populations don't change. So this equals 0 at thermal equilibrium. It equals 0. And the other thing that we know is that, as we said, we know the ratio of N2 to N1. So I can take this equation and I can divide it by N2.
Can I ask a question?
You may, but let me just conclude this just very quickly. So what will we have here? We'll have here minus a to 1, or let's invert the sign. Let's forget about the minus. So a to 1 plus b to 1 u minus n1 divided by n2 times b1 2 u equals 0. Or I can write u equals, and then we should remind ourselves that this, sorry, I didn't mean to do that. This equals to e to the minus h bar beta beta h bar omega. And we can extract u out of this, and we'll find it as a to 1 divided by b1 to e to the minus h bar, beta h bar omega minus b to 1. Okay. Yeah, what was the question?
It seems like you assume linearity in time here, or is B and A kind of complex functions?
Why should they be complex? We're discussing some rating.
Not complex with I mean like functions in time.
No, we assume, I assume that the response is linear. That, and indeed, well, no, in most cases it is. It is true that you could have.
I can even artificially made one. If I like take a laser cavity and I charge it, sometimes I charge it, sometimes I take a laser cavity that you physically charge electricity into it. Then I give it pulses of electricity. Like,
oh, but then you're driving it. I mean, if we're talking about here, you have a set of atoms. All they are doing is they're sitting at a specific temperature.
Still, you can assume there's a development in time. It's not something radical. Maybe it starts as a specific state. Let's say everything is stimulated and then slowly drops down.
But we're talking about, okay, but let's assume, I'm not talking about anything transient right now. And there are many things that this model does not include. This is not a true quantum model. This is the simplest model you can think of, which basically says, okay, I have some atoms that are excited because they absorbed some light. I have some atoms that are at the ground state because they didn't absorb light or because they were stimulated down by stimulated emission. They can also fall down by spontaneous emission. And now I assume that the atoms are in thermal equilibrium. What does this tell me about if the atoms are in thermal equilibrium, what does this tell me about the average energy density of the field at frequency omega? And it turns out that this means that, okay, so this is what it is. But on the other hand, we can do that from Planck as well. I mean, this is something that we know from Planck, what it is. It actually is this. It's or from Planck, black body, we can write this u of omega d omega. This is needed because in the case of this is what is this? This is the, in Planck black body, the radiation is continuous. There is no specific frequency. So we can ask ourselves, what is the density here? So this is what we would write. We would write that this is equals to N average times H bar omega, which is what we assume, times the density of states at omega times d omega. And this is what? This we can write. And this is, so there will be, this is 1 minus 1, or let's start with N itself. Just N itself, this is, we know, we calculated. This is e to the minus beta h bar omega minus 1. This is N. And then basically it will be times h bar omega to the power of 3 divided by pi squared c cubed. And there will be d omega here. Now we assume now that we're looking at there is a range d omega which suits here. Oops. So look, we're talking about those two. The only possible way where those two would agree is if there's really only one coefficient. So B12 and B21, they must be the same, and A must be related to them. So that means that by definition, B12 equals B21 equals some B. Okay. To reconcile the two equations, it must come out that this is this, and that A is also related to B. It's just this, h bar omega power of 3 divided by pi squared c squared c to the power of 3 times B. So there really isn't, when that means from very simple analysis, you understand that there's only one coefficient. There aren't three. The Einstein coefficient, there is a strong relation between the coefficient of stimulated emission, the coefficient of absorption. Those two are exactly the same. Actually, this you can prove classically also, because the electromagnetic field is a real field. And then I'm not right now explaining this, but this is easy, and we'll see this happening very soon, where we actually discuss absorption from a physical manner. So this fact, this is really no surprise. We'll see this next week, I promise. Maybe we'll start this week. But this one is a surprise. The spontaneous rate is not just related, it is the same as the stimulated rate. The coefficient that you have here is just to get the dimensions right. Spontaneous emission and stimulated emission are somehow strongly related. And we don't know where spontaneous emission comes from. It will take us, as I mentioned, a while to understand. Because to understand where spontaneous emission comes from, we will need the vacuum. The fact that the electromagnetic field, when there is no field, it's not really zero. There is a vacuum state that is very surprising. It's like the ground state of a harmonic oscillator. And the fact that the electromagnetic field is related to harmonic oscillators is not very surprising. But, you know, the ground state of a harmonic oscillator, if it's a classical harmonic oscillator, it's just zero. The particle is sitting at the bottom. but quantum mechanically it does not. And this, so there is something surprising. There is electromagnetic field in the vacuum. The no field is not nothing. So to be consumed by the nothing, if any one of you saw the never-ending story, it really does mean something. Okay, so this is the, for this, there is no classical explanation. Now, okay. So there's really just, as I said, there's just one coefficient, and you can say that I can ask myself, what is B times U at thermal? So this is, we're talking about at thermal, at thermal equilibrium. We can write that this equals A times the average N that we had before. Or, and this is the absorption probability, and B times UT plus A, which equals A times this N average plus 1. This is the emission probability. Now this is the total emission probability. This is the stimulated part, and this is the spontaneous. Now, all of this N and N plus 1, those are things that appear in quantum field theory a lot. But look, all we had here, N is some kind of an average over the average number of quanta that exist in a specific mode. Okay. Now, by the way, you can use, okay, yeah, we finish soon. We can, for example, ask ourselves what happens for yeah. And then, so we can see out of this that basically A divided by, so the probability of spontaneous divided by the probability of stimulated, so spontaneous. The question is, what is more likely, to have a spontaneous event or a stimulated event? The answer is this goes like 1 over the average number of photons, not photons, quanta emitted. The average number of, you know, it's the average energy, but it's the average energy measured in units of h bar omega. And what is this? Well, and then this is what we get. And it equals e to the minus beta h bar omega minus 1. And then we can ask, okay, so who dominates? Does the spontaneous emission dominate or the stimulated emission dominate? Well, it depends on the frequency, of course. If we ask ourselves, okay, so when is this equal 1? This is where they are both contributing the same. So I ask myself, and you can see that at low frequency, the stimulated part dominates strongly because the average n is large. But at high frequencies or in optical frequencies, the average n is very small. So the spontaneous term dominates strongly. So, you know, well, all it means is that e to the minus beta h bar omega equals 2 or beta h bar omega equals ln 2. And then I can ask myself, what is this? So, and I'll tell you what the temperature is. So, yeah. Assume K. Boltzmann, you know, T equals 300 degrees Kelvin. And you can ask yourself, in which frequency is this happening? You'll get that the omega of equality equals something like, is of the order of 10 to the 13 hertz. Or 10 to the 12, but it doesn't. Oh, okay, I'm sorry. 10 to the 13 hertz. Okay, that means that if you are in radio frequency of megahertz or gigahertz, then the thermal emission dominates strongly. You can completely neglect spontaneous emission because the number of quanta per mode is huge, the thermal number of quanta. But if you look at much higher frequencies, optical frequencies, which are of the order of 10 to the 15 or 10 to the 16 hertz, there the situation is the opposite. The number of quanta per mode is tiny. It's less than 1 over 100. And the probability of stimulated, probability of stimulated emission by thermal radiation around you is practically none, 0. So for omega much larger than 10 to the 13 hertz, spontaneous dominates. So this is the case in optics. Usually, it's very hard to generate a field with a very high density of energy, enough to, okay, well, yeah. I think, so let's say just one thing about this. So the rate equations that we had before, they're useful also outside of thermal equilibrium. So now we want to, using the A and B coefficients outside of thermal equilibrium. What can we do? Well, we have those rate equations. They are correct. I mean, I can have, you remember, I have this dn2 to dt, which equals minus dn1 to dt, which can be written as minus a times n2, and a and b are related, but I still write them as different, plus what? Plus, we said n1 times b times u, minus n2 times b times u. Okay, but we can write, say, n1 as being n minus n2. So we can write this entire thing as a times n2 plus n minus twice n2 bu. Now tell me what u is. So this is a differential equation. Tell me give me what u of t. You know, if I'm given some u of t, and if I'm given n1 and n2 of t equals 0, I can solve this differential equation. It's rather simple. Well, I can actually solve it immediately, because if you look at this, this can be directly, I can write from here, I can immediately write dn2 divided by an2 plus n minus twice n2 bu equals what? dt. And this can be solved. Or I can write or dn2 divided by a plus 2bu times n2 plus 2bu, not 2. nbu, that equals dt. And there is a solution to this. There's an immediate solution that tells you that, there won't be enough space, so we'll write it here. Minus 1 over a plus 2bu times ln of something. n2 at time 0. Well, you know what? It doesn't really matter. I mean, this can be solved. I'll tell you that. I'll just give you the final solution. n2 of t equals what? Tell me what n2 at time 0 was. Minus nbu divided by 2bu plus a times e to the minus a plus 2bu times t. So there is some exponentially decaying term, and there is some constant term, nbu divided by 2bu plus a. Okay. So this is, no, that's not what I wanted. this is as a function of time. Tell me how u is. This is assuming here. This is a solution that assumes u equals constant. But the initial condition is not necessarily constant. So for example, we can ask ourselves, what happens if, as a function of time, let's say that N2 in the beginning was 0. All atoms were in the ground state. So N2 was initially 0. Then we'll have something that goes like charging of a capacitor. It will exponentially go to this value of total N times BU divided by twice BU plus A. Well, what does it mean? It means, for example, that the total population of the excited state can never be more than half. And this, this time scale it's like tau equals 1 over A plus 2 BU. So this time scale, so there is a time scale. If you have a lot of light, it will happen fast. If your energy density is low, it will happen slowly. And now is a good time. Okay, so I should finish. Actually, I should have finished something like 5 minutes ago. So, but this is a good place to stop, because that means that, for example, N2 is always less than total N divided by 2. According to this, no matter what you do, eventually, there will not be more than half the atoms in the excited state. It will always be less. Only so if U goes to infinity, then N2 goes to half N. There is no population inversion in a two-level system. That's actually correct. Those rate equations are very, very useful. They're very useful for lasers. We're not going to say much about this. There are very strong conclusions that you can make from this very simple model that we discussed today. You can solve these equations in many scenarios that you can think of. And this is a correct result, though there is something that we didn't think of. And that is, this is not a quantum model. This is a probabilistic model. There is no superposition here, but we know that an atom can be in a superposition of excited and ground. And this superposition can be with a positive sign or a negative sign. It can be A plus, excited plus ground, or excited minus ground, and it makes a lot of difference. So this quantum coherence was out. So we can ask ourselves, what did we miss? The answer is coherence and interference, quantum interference within matter. We discussed only probabilities of being either excited or ground. And this we'll discuss next week. So we will do a much better quantum model of the two-level atom interacting with a field, and we'll discuss how this actually evolves and how coherence plays a role. So this is the one thing that we missed here. But the Einstein model is very useful for many things in optics and in lasers. The rate equations of lasers are basically based on this Einstein model and generalization of it. And sometimes, as long as coherence is not a critical point, it is actually very useful and okay to use it. So those limitations and where they are broken is what we will discuss next week. And with this, we will conclude our meeting today. We'll let you rest for 20 minutes until you start the tutorial. And you can discuss with Leon the possibility of moving the tutorial to a more convenient time. That concludes our meeting. If you have questions, I'll be happy to answer. No questions whatsoever. Everything is so clear. I'm glad. Okay. Thanks for being here. I hope you'll enjoy the course. I hope we'll get to meet in person. Please don't be afraid to ask questions because there is no such thing as a stupid question. But those who do not ask questions that they think are stupid don't get smart. Okay. So with this, we conclude. I'll tell you goodbye.
Avi.
Yeah.
It's not a question, it's a request. Can you please upload your notes to the Moodle?
Yes. I will. There is, I'll tell you what is happening. There is, on the cloud, there is a directory that you have a link to. In that directory, I will put all the recordings of our meetings and also all the notes.
Thank you.
So for every meeting, there will be a recording and the notes.
Thanks.
Okay. Good.
Thanks.
Ciao.
Bye. Thank you.
Bye-bye.